Hi, so we're starting the second session. So we have two papers and followed by a panel discussion afterward. So let's start with the papers.
Hi everyone, I'm Brian Liu and my advisor is Dr. Adam Perrer. Today I'm going to present our work in interactive interpretability system for breast cancer screening with deep learning. To provide a little bit of background, deep learning algorithms, and in particular convolutional neural networks, have achieved remarkable performance in various medical image computing tasks, such as classifying mammograms for breast cancer screening. However, deployment of CNNs in medical domain face challenges due to its black box nature. Thus, it's critical to empower domain experts to interactively understand the model's decision-making process. To tackle this challenge, both the visualization community and the machine learning community have made great progress. For example, multiple visual analytics interfaces has been proposed for models in various healthcare applications to improve understanding and supporting clinical workflow. On the other hand, machine learning and computer vision researchers continue to propose novel methods to visualize and interpret convolutional neural networks. Inspired by this progress, we want to leverage a generic yet powerful methodology, network dissect, which aims to decode semantic meanings of individual units in CNNs to support clinical workflow integrated with deep learning models. While the method was originally proposed as a way to quantify the interpretability of neural networks in an overland setting, we think it can be a promising gateway for medical professionals to interactively probe the learned representation and inspect the model's decision-making process. In particular, we focused on the task of breast cancer screening. Previous work has shown that we can train a patch-based CNN to tell whether there's lesion or potentially the cancer regions in the mammogram. So the question is, given a binary classifier that differentiates lesion versus normal tissues in the mammogram, how can we integrate state-of-the-art interpretability technique to the radiologist-model interaction to maximize their complementary set of strengths? To tackle this question, we propose to implement an interactive interface to allow the radiologist to understand the following when given a decision of our decision model. Firstly, where does the model focus on in this image? And secondly, does the model pay attention to region X, where the radiologist deems important? More specifically, our approach views the model output as a combination of each unit's or convolutional filter's learned representations. So the first question translates to what's the unit that gets the most activated and what does its activation map look like? And the second question translates to are there units with activation map similar to the user-defined region X? And do these units capture certain features consistently? Here is a central interaction design in our interface. Given a user-defined region deemed important to the diagnosis, we want to check if there are units that activate on similar regions, or in other words, pick up similar concepts. And the metric we use is intersection over union. To assist the exploration of units' learned representations, we propose an embedding to visualize connection between units. So given a test set X with n samples, we can compute the maximum activation value on each of the n samples for each unit. Suppose we have m units, we will end up with an embedding of shape m by n. And for visualization purposes, we can apply PCA with two and select two components, thus generating a matrix of shape m by 2. As we can see, each point in this scatter plot represents a unit in the last convolutional layer, which has shown to be the most semantically meaningful. The functionality we built into our interface is to allow users to label units along the way as they probe the model. This design is inspired by a finding in a network dissect paper, which states that object detectors can emerge in convolutional neural networks. So basically, when a CNN is trained, for example, when a CNN is trained to classify scenes, individual units can actually pick up high-level concepts such as people, tree or chair that make up these scenes. So while our classifier is only binary, it's possible that those neurons may have picked up more fine-grained subcategories or concepts of vision, such as mass classification. And in our interface, we allow the user to label the semantics of units conveniently as they check if the model pays attention to some features it deems important. Then the unit annotation can be used to provide finer-grained summary about the model's prediction in subsequent images. A quick demo of our interface. On the left, we can see the mammogram to screen as well as the lesion patches found by our model. When we click on a patch, we will able to see where the lesion is in the mammogram, as well as the activation map of the most activated unit in our model. Suppose the radiologist doesn't think this unit captures the most important feature that defines a lesion prediction and wonder if there is a unit that focuses instead on this region. What our interface does in the backend is that it compares the overlap between the user-defined map and activation maps of all other units. After that, units whose activation map has high overlap will be highlighted, so that the user can click on them to see the top K activated images associated with these units and confirm their consistency in capturing specific concepts. Once the user is convinced, they can label the relevant units. These unit annotations can then be used to provide additional statistics when the model predicts on other images. This way, the user can progressively endow the model with additional knowledge naturally in their workflow with little labeling overhead while being able to probe the model's representations. For next steps, we think it will be valuable to interview radiologists to see if our interface truly benefits their diagnosis, for example, in terms of efficiency or transparency. Also, we think it's important to quantitatively evaluate our proposed unit annotation strategy to see how effective these units are to pick up finer grade concepts. Finally, I would like to acknowledge the support and help from my advisor, Dr. Adam Perrer, who is co-director of the CMU Data Interaction Group. I provide a link to my code, which is now open sourced. Our work has used the Bridge 2 system, an NSF self-supported project at PSC. Thank you for watching my presentation.
We have some questions from the Slido. I'm going to start with the first question, Brian, if you can answer it. What do you think of an idea using user feedback to steer or improve the model? Have you thought about that idea?
Yeah, sure. I think that's a great question. And right now, we're mainly leveraging the emergent capabilities of deep neural networks. It's kind of we train a network and hope to see it adopts or picks up some fine-grained concepts. It's kind of a post hoc thing. We didn't really enforce anything, for enforce network to learn any specific concepts. So I'm thinking as maybe a few shot learning strategy can be used to, probably to steer and improve the model because, the labels for these finer grade concepts might be very, very few. So that's why I thought, few shot learning or active learning strategies might be helpful in this case to steer or improve the model. Yeah, that's kind of our future steps, probably.
Yeah, thank you so much. In the interest of time, so we have more questions, but let's do it on Discord, and then let's continue to the second talk of the session.
All right, thank you.
Hello, my name is Klaus Eckelt and I'm a PhD student and doctoral researcher at the Johannes Kepler University in Linz in Austria. I'm presenting Kokiri today, a visual analytics approach to compare and characterize cohorts. With a random forest, we try to classify the cohorts based on user-selected data and rank attributes by their importance to distinguish between cohorts. We show how well patients were matched to the cohorts and the probabilities of the patients to belong to the individual classes, once in a detailed list and once by projecting them to a scatter plot for overview. This way, we give an overview over the cohort separability, what makes them separable, and how homogeneous the cohorts are with respect to the data. The idea for Kokiri grew out of Coral, an application for creating and characterizing cohorts. In Coral, we can easily define cohorts based on genomic or metadata, but comparison is limited to one or two attributes. We have already integrated Tordino in Coral, where cohorts can be statistically compared based on user-defined attributes. But the cohorts are compared by each attribute individually, so their overall separability cannot be judged, and also combinatorial effects of multiple attributes are not considered. We have also seen this limitation in many other works, and have therefore created Kokiri to compare cohorts by the high-dimensional data and find the driving differences between them. We have integrated Kokiri in Coral to make use of its cohort creation and characterization functionalities, and I will next explain Kokiri based on a use case we have also described in our paper. For that, I'm going to start from a previous session in Coral in which the user created cohorts of non-small cell lung cancer patients of different race and gender. A recent study has shown differences in the KRAS mutation frequency between these cohorts. And by using Kokiri, we want to investigate whether there are any further mutational differences. We start by selecting the 6 cohorts and select the characterize operation which integrates Kokiri in Coral. As the cohorts are created by splitting the data into distinct subsets, the overlap view only shows a short note that the cohorts do not overlap. I will show an example with overlapping cohorts later in my talk. In the next step, we can compare the cohorts by their metadata or the genetic mutation frequency. By default, the comparison only considers attributes that were not used to create the cohorts. We compare the cohorts by mutation frequency, which starts training a random forest model to classify the cohorts based on the high-dimensional data. We gradually increase the number of decision trees in the forest and show intermediate results to give users early feedback on cohort separability and important attributes. The interface of Kokiri is divided into 4 sections, and the cohorts are represented by color throughout all sections. At the top right, a stacked bar chart shows how the patients are matched with cohorts. For the 6 lung cancer cohorts, we can see that most items are correctly assigned to the white female and male cohorts, which are also the 2 largest cohorts. However, also large portions of patients from the other cohorts are assigned to these 2. In the table on the left, we rank attributes by their importance in the random forest model. The first results show that the genes TP53, EGFR, STK11, KRAS, and FGFR4 are the most different between the 6 cohorts. The column on the right shows the distribution of that attribute for each cohort. These are all categorical data and we therefore use a bar chart. For gene mutations, the bar chart shows for each cohort how many patients have an amino acid mutation for that specific gene. For EGFR mutations, we can see differences between the gender, but there's also a huge difference between the 2 Asian patient cohorts and the others. Noticeable is also the distribution of FGFR4 mutations, where the bars are hardly visible. We further investigate the distribution of FGFR4 mutations in Coral's view operation. There, we can see that there is indeed little difference in the number of mutations, but that gene is sequenced much less frequently for the 2 black cohorts. This could point to possible issues in the data, and we will look into that later in my talk. Next, we further analyze the trained classifier with the characterization view in Kokiri. The table on the left lists all patients, the cohorts they belong to, and by which probability they belong to that cohort according to the classifier. We also have the highest probability as a separate column to quickly judge whether the model was sure or unsure about this item. On the right side, these probabilities are summarized in an embedding scatter plot. We project the probabilities to 2 dimensions with supervised UMAP. The scatter plot shows 1 point for every patient, colored by the cohort they belong to. And in the background, we plot a heat map that shows the cohort with the highest prediction probability with that cohort's color. The heat map's opacity decreases with the classifier's confidence, so when the probability of the predicted cohort has little difference to the others. The scatter plot shows a distinct cluster for each of the 6 cohorts, but also many smaller clusters as well as single items. By hovering over one of the smaller clusters, we see that the probability for the assignment to the Asian female cohort was just 25.7%. We select the items in this cluster, which also selects them in the item ranking, where we can see probabilities for all other cohorts. Even though the items in this cluster originate from the different cohorts, the prediction probabilities are very similar, suggesting that the data is similar as well. This could be a point in the analysis where the user leaves Kokiri and defines new cohorts based on the findings, or investigates individual items in more detail. But in the remaining time of my talk, I want to look into another finding we had, which is that FGFR4 is sequenced much less frequently for Black patients than for the other cohorts. With Kokiri, I want to compare the Black patient cohort with the overall lung cancer cohort to see if there are any other differences there. The overlap visualization now shows that one cohort is a subset of the other, the difference in size and the overlap size. In the attribute importance table, FGFR4 is now ranked the highest to differentiate the cohorts, and BRCA1 shows a similar pattern in mutation frequency. It is also sequenced less frequently, with about 50% of the data being unknown for Black patients, while it is just 25% for the overall lung cancer cohort. One reason for this may be the huge differences in how comprehensively genomics data are collected at the different sites where patients are treated. The prediction table at the bottom now only shows that items belong to multiple cohorts. As a next step, we would like to combine Kokiri with low-dimensional embeddings of the high-dimensional data. On Friday, I will present our work on the exploration of structured data in low-dimensional embeddings. There, we already have a ranked list of attributes to highlight differences between groups in the embedding, but the attributes are considered individually and not in combination. That is, however, only one part, and I hope to see you on Friday where I can go into more detail. With this teaser, I would like to end my presentation and invite you to check out the paper, code, and application via the QR code and link on the last slide. I look forward to answer your questions and discuss ideas online or at the conference in the upcoming days. Thank you.
Thank you so much. We have a couple of questions, Klaus. Great work. First question is, if you have any form of user study already conducted or interview, and what was the general comments? And I'm curious how difficult it is for them to learn how to use it.
Yes, good question. Thanks. So Kokiri is part of Coral, and we already worked on Coral for a couple of years now, together with our collaborators from that work in drug discovery, and they are also co-authors for the paper. And we have regular meetings on a 2-weekly basis where we exchange things, and they're also rolling out the whole tool in their company. And so they already know the application where it is embedded, and we try to stick to the interactions that we already use there. So they also use to this lineup ranking and the charts and this cross selection. And we only had feedback from the 2 co-authors, and that was good so far. But I'm of course curious how it will be with additional people that were not involved so closely in the design process.
Thank you so much for your answer. So there's another question, but we already, it's 11:05, so let's move on to the panel discussion. which will be moderated by Chen-Wen. Chen-Wen.
Yeah, great. Let me share my screen very quickly. Sorry, how to? Sorry. Okay, can you see my screen? Like people on site? Well, let's just welcome to the panel discussion of visualization in biomedical AI. And we are super excited to have invited Adam Priya, Mark Street, David Gotts, and Marinka Ziklik to join us as our panelists. They're all excellent researchers whose expertise covers different perspectives from visualization, machine learning, biomedical, and healthcare applications. And for this panel discussion, we will have two parts. In the first part, we will have a panel presentation for each of the panelists, and then we will have a 30 minutes discussion. And for the discussion, feel free to ask questions in Slido. We will try to answer them in the discussion. And also, I want to mention that we will have a launch meetup to continue the discussion face-to-face after the workshop, and you're welcome to join us. Niels and BC will be in the room to help coordinate. Yeah, so let's start.
Okay, hi everyone. Let me just get my thing set up. Hopefully everyone can see my slides. So hi, I'm Adam Pear. Thanks for the nice introduction and thanks for inviting me to be on this panel. I'll try to keep this short so we can get into the interesting discussion part. But my name is Adam Pear. I'm a faculty member at Carnegie Mellon University, and I co-direct this data interaction group inside our Human-Computer Interaction Institute there. And I guess one general theme of the work that I've been trying to do over the past handful of years is lots of clinicians are surrounded by data, and oftentimes it's very unclear how to leverage this data to actually help improve the decision-making decisions inside the healthcare context. And oftentimes we can kind of be overwhelmed by this data and will actually help us or hurt us when we're trying to make decisions. And so what my lab tries to do is we try to build these tools that can give us kind of clinician superpowers so they can kind of find these patterns in the data and maybe make better decisions. But we also have to be very careful that we don't accidentally turn them into supervillains where they're kind of misled by kind of the simplifications of the models and or the data transformations that we do on the data. So again, really focusing here on these kind of superpowers. How can we kind of leverage them? And over the course of a bunch of years working in the healthcare space, built lots of different types of kind of visualizations and tools and techniques to really help kind of visualize the high dimensional healthcare data, or how to even visualize and interact with AI predictive models. And some of these tools that I kind of just flash on the screen here are actually done with some of the other panelists or co-organizers of this workshop. But I want to kind of focus on some new stuff that I haven't had a chance to talk to you about yet, that I think might motivate some of the stuff that we can have in a discussion later. So this work isn't, hot off the press. It's not even in the presses yet. But again, I really thought I'd tell this story to maybe motivate some of the discussion that we'll have later. So this work is led by a PhD student that I advise, Venkat Sevaraman, and some really interesting work he's been doing in the intensive care unit of hospitals in Pittsburgh, which, let me tell you, is a fun place to be during COVID. But today I'm going to be talking about sepsis, which is this thing that occurs when kind of their body's response to an infection injures its own tissues and organs. And this is a final common pathway to death from infectious diseases for lots of people. Here in the US, it's about almost 2 million cases per year. But how do you make a diagnosis of sepsis? Typically, you make it by either looking at symptoms, things like blood pressure or fevers, or lab tests, things like blood cultures. And there's different ways to kind of treat sepsis, and to be honest, the best practices for these treatments are continually evolving. So here in the ICU, as you can maybe see on the screen, there's lots of data. There's even some data visualizations. So is data visualizations kind of driving decision-making in the ICU? Well, according to our interviews, not quite. Early diagnosis is essential to reducing mortality. So looking at data can help, but it's not driving decisions. So is AI driving decisions in the ICU right now? Not the case quite yet, although there has been a lot of interesting progress in that field. And so, for instance, there was this kind of really interesting paper in 2018 called the AI Clinician, published in Nature, and they showed really promising results that their algorithm could kind of, the mortality was lower for their patients than what actually happened in clinical practices, which was very exciting. And there was lots of press about it since we're an IEEE workshop. There was a nice article from IEEE Spectrum that was like, we're not just making the AI see like a doctor, we're making it act like a doctor. So there's all this promise of kind of actually integrating AI into the clinical workspace. But now this paper is now 4 years old. Are any ICUs actually relying on this algorithm? Unfortunately not. And why is that? So that was actually what we wanted to do. And so what we actually did was re-implemented the AI clinicians reinforcement learning algorithm. So it would take historical data, again, plug in 48 different features from all the different patients, have it try to recommend up to one of 25 actions, which is how the algorithm was really designed for kind of different dosages of fluids or vasopressors. And then again, the algorithm kind of gets a reward if the patient is discharged or a negative reward if the patient leads to death according to this respective data. So you end up with this train policy, which is exciting. But what we are really trying to understand is how does AI and or plus or minus visualization kind of impact decision-making in the ICU? And so again, we kind of re-implemented AI Clinician, and then as data visualizers, we designed visualizations that describe the patient data going into the algorithm, as well as the visualization data coming out of it, right? Trying to create effective explanations of the models. And then we gave actual, 24 real ICU clinicians interesting and complex use cases with real data. And so I'll kind of just give a preview of some of the results that might spark some discussion. But when the AI predictions were shown alone without any visualizations or explanations of the results, clinicians might ignore the predictions completely, or on the other side, trust them blindly. In either case, that's not really super optimal. However, if we did provide visualization-based explanations, the most common pattern for these decision makings was actually some sort of negotiation between the AI predictions and the clinicians. Clinicians often sometimes modify some aspects of the decisions that they kind of mentioned before seeing the AI explanations, and then take some of those results and kind of integrate them into their final decision. So I don't have time to go through all the results right now. I thought I'd just leave you this kind of tidbit to kind of demonstrate how important visualizing the data and visualizing the model can be, particularly as these algorithms are becoming more and more prominent. So with that, let me hand off to the next speaker. Thanks for listening.
All right. So thank you, Adam. That was a great view into some of the work you're doing. I am David Gotts at UNC Chapel Hill, and I'm going to talk about some of the work that I've done, which did appear in that screen that Adam mentioned with some pictures that were with collaborators on the panel. So just to kick things off, the group I lead here at UNC is the Visual Analytics and Communication Lab, which does research at the intersection of visual analytics, of course, but also human-computer interaction, machine learning statistics, and a lot of applications to biomedicine in different forms, and other data work in other disciplines as well. Given that focus, we have an interdisciplinary group. So my home at UNC is in the iSchool, so information science. I also advise computer science and health informatics students and work a lot with biostatistics, medicine, and public health. And in all of our work, what we try and do is start by understanding how people model, learn from, or take action from complex data using visualization or other computational tools, and then try and figure out where things are hard or where things might go wrong, such as drawing the wrong inferences from their data or not even being able to use their data at all. And that leads us to develop new methods. And we've tackled problems from the whole range of the data workflow, if you will, starting from issues of data quality all the way up to how people derive visual inferences from the visualizations they look at. Once we develop those, we try and apply them to real problems in clinical medicine, public health, or other domains that are driven by data. So just a quick overview of a few projects before I dive into one. We were asked to talk about our success story, if you will. So, we've applied machine learning to do classification and detection of arrhythmias from ECG, long-term data streams, We've also done work with pattern finding and prediction for disease flare-ups with longitudinal mHealth data like Fitbits and Apple Watches. A lot of these look at clinicians as users, and we've found a lot of challenges in that domain. So it's actually one area I might not put in our success story, so we can talk about some of those challenges as we go. Some of the places where we've made a little more progress are working with population health analysts. And so we've created tools for building predictive models and evaluating them, even some that's gone into product at IBM back before I went to UNC. And the area where I'll highlight as a potential success story is our kind of long-term focus on event sequence data. And this is where you might recognize a screenshot from the previous presentation, where about 10 years ago, we first published an outflow paper at Viz, where we were looking at temporal patterns and trying to look at patterns over time and how they associate with medical outcomes. And that was a pretty simple data set with a relatively small number of medical events, and we were looking at sequential patterns. And over time, we've built up a number of different ways to deal with complexities of real-world problems in this area, dealing with high dimensionality, mining of patterns, predictive modeling, identifying multiple cohorts and comparing them, quantification of selection bias as we apply filters and narrow down into small groups, as we heard in the last research presentation. We also looked at extracting stages of disease progression, even causal modeling within our data. And that gave us kind of a toolbox and some prototypes where we can rapidly apply some of these tools to do population health analysis. And then we landed a couple of years ago in COVID, where all of a sudden we had a bunch of people who were really interested in trying to understand a novel disease with data that we were collecting from the health system. And we were very quickly able to rapidly deploy the technologies we were building over those years to a large cohort of COVID data from the UNC health system and start to identify key risk factors and other patterns. And sure enough, we were able to quickly identify things that then ended up in the scientific literature when people used kind of more intensive long-term research procedures that are kind of done more traditionally. And we felt this was kind of a validation of some of the techniques that we've been working on. So with that, I'll stop there and we can talk about some of the challenges with this approach later on.
All right. I think it's my turn to continue. My name is Marc Streit. I'm a professor at Johannes Kepler University in Linz, Austria. And I also want to start by saying a few words about the kind of research we do. And by we, I mean all members of the Visual Data Science Lab at JKU in Linz, Austria. We basically work on problems that concern the interplay between automated techniques and interactive visualizations. And I'm also the CEO and co-founder of DataVision, which I founded together with Niels Gillenborg, Alex Lex, and Sam Gratzel a couple of years ago. And the team at DataVision works on database solutions for the pharmaceutical industry and also biomedical R&D. So I can reflect on lessons learned from research projects, but also from professional solutions we created for industrial partners over the years. And as many of you, I started to work on AI-related problems several years ago. And at that time, XAI was mainly about opening this famous black box of machine learning, right? And at the beginning of this hype, XAI was mostly done by machine learning researchers. And you really find explainable AI papers with lots of formulas without any visual representation. And to me, it always felt a bit like inmates running the asylum. And this actually goes back to the book published by Alan Cooper, who made the point that software is often designed by engineers instead of UI experts and designers. And I think the same applies to XAI, which was later also formulated by Tim Miller. And this view has changed in recent years, and now people, I think, are more aware that XAI includes other aspects that lie outside of this box, like psychology, cognitive sciences, philosophy, law, and so on and so forth. And 2 weeks ago, I actually co-organized a one-week workshop on AI in medicine held at JKU Linz. And the students had mixed backgrounds, including AI, computer science, medicine, and even law. And it was super interesting to see them interact, because at the very beginning, they were not even able to talk to each other, right, about the subject, of course. And at the end of the workshop, they had a better understanding of the challenges in the respective other fields and were also able to speak some kind of common language. And I think key is always understanding your target audience. And well, there was this discussion is going on in our community for a long time. You can cater to those different audiences, model developers, model users, decision makers, and so on and so forth. And I want to just highlight a few of our recent projects. One is together with Hendrik Strobold from IBM Research on a system called Confusion Flow. And it was basically to understand the training process of classifiers and to compare them with each other over time. Another project, or like a family of projects we're working on, is about making embeddings more understandable and easier to explore for domain experts. In this case, here on the screenshot, biologists and bioinformaticians. And Klaus is actually going to present a paper in the comparisons session on Friday also. And this is clearly about like targeting domain experts. But we also have other projects which is more about targeting model users. Like this is one collaboration with Bayer, and it's about actually cheminformatics. And you have a model that predicts the properties of chemical compounds. And again, we try to explain then like what contributed to the prediction, like whether the compound is solvable, whether it's toxic, and so on. And you can even see like that there is oops, let me move that away. Like there are like positive and negative contributions to the prediction. And the last project I want to show you is a bit off topic, but the target audience are lay users. And it's about using an app that is able to predict whether a mushroom is edible or not, right? So this was, we did actually a study with over 300 participants at the Ars Electronica Multimedia Festival. And the goal of the study was to compare different explanation strategies. You could also apply that to like high stake decision-making task in like the medical domain. And one of the key factors of the study was also the role trust plays, because people overtrust or undertrust in general, but also have that in AI systems. And one of my main learnings is that explainable AI is so much more than opening the black box. And the second learning is really that solutions we provide as a community are often too complex and I think too technical. And basically, if you move down the list, it needs to get less and less technical because also the AI knowledge is getting lower and lower. And this basically echoes also what Kerry said in the keynote at the beginning. Well, I'm looking forward to an interesting discussion. And with that, I give the word to Marinka.
Thank you so much. Let me start by sharing my screen. Okay, great. Really happy to be here with everyone today. Thank you. Thanks to the organizers for organizing this workshop. My research group at Harvard Biomedical Informatics is focusing on developing core new foundational machine learning methods for problems in medicine and science. And on the medical side, we are primarily driven by questions of individual diagnosis and therapy recommendation. And in the context of scientific discovery, we're really interested in how to make the process of discovering safe and effective therapies more efficient and accelerate it considerably, and think about ways for integrating AI in a thoughtful, careful manner into the scientific process. And so in the next few minutes, I'd like primarily to focus on the second component or main direction of our group, and that is really recently driven by an open science foundation we created called TDC, or Therapeutics Data Commons, that serves as a meeting point between, on one end, machine learning scientists designing new core algorithms, and on the other end, domain experts, biomedical scientists, and biochemists in this context, who identify meaningful machine learning tasks and meaningful data sets that are at the cusp of benefiting from a machine learning analysis and can help facilitate both algorithmic innovation as well as advanced therapeutic science at large. And so to this end, the way TDC works is that provides a rich ecosystem that can support machine learning workflows throughout stages of drug discovery, going from formulation of machine learning tests to sourcing, harmonizing, and standardizing relevant data sets, and then to developing most recent algorithms using deep learning frameworks, evaluating their performance and deciding what is the method that is best in class method that can transition into real world and practical implementation. Now, as part of that, for us, it was really important to be providing this ecosystem that covers a broad range of different therapeutic modalities, from small molecule drugs all the way to cell and gene therapies, as well as antibodies and peptides, and really be very thoughtful about how to benchmark and evaluate model performance to decide what models are ready to transition in real world implementation. And so, as someone who is very strongly grounded in machine learning method development, our ways of benchmarking models often entails carefully designed non-random data splits and a variety of statistical and performance metrics that constitute established strategies in machine learning research. However, being involved in therapeutics data commons, there's been increasingly important for us to think about ways for our end users to interact with models provided and implemented in the commons. So there are a variety of models that constitute interesting use cases of the commons throughout stages of drug discovery, from predicting molecular properties in early drug design to identifying what are therapeutic targets that can bind to certain molecules associated with the diseases, to techniques that can support late stage of drug discovery and development, even situations where drug is already on the market, and we are exploring ways to repurpose that drug for novel uses or for emerging pathogens and be able to model their therapeutic use more comprehensively. Many of our interactions with the domain users are then often involve users who are not necessarily developing machine learning models, but are really smart and want to use the models in their everyday life and also be able to integrate their own data into these big, large graph neural networks, language models that we're developing that are trained on broad public data at scale. And so to support that kind of user interaction, we've been increasingly relying on designing visual interfaces, such as the one shown on the left, that uses Gradio actually to quickly integrate machine learning model outputs with the machine learning model itself, and then support interactions with users. So what I'm showing here on this slide is an example of an interface that provides for a user, when they input a given molecular structure and a given sequence of a particular protein that might act as a therapeutic candidate, and the user was then interested in knowing what are the molecular properties of that molecular compound and whether that compound would bind effectively to the therapeutic target. And so the output of the models would inform in a sequential manner the next steps of the analysis and would even require the user to be able to change and manipulate the molecular structure and see how that changes model predictions. And so in that way, models can be improved over time. So as part of that effort, some of our work is concerned in really developing core algorithms that can explain user predictions, not only provide point-wise estimates of those predictions. And so here I'm just showing an example of a query that user might ask, which is whether a form of statin would treat hyperlipidemia, what could be a disease-driven mechanism for that. And so the model, as part of their analysis, and the explainers we are developing would return not only predictions, but then would highlight part of the input data, which can often be complex interaction graphs that drive the model to make a particular prediction, identified in using counterfactual inference algorithms. And so one of stories that I think is a success story, and I will conclude with that, is really the question of, can now these explainability methods really help us discover new principles of disease treatment and disease, and in this case, of viral infection? So recently, our algorithms from Therapeutics Data Commons were used as part of the National Task Force to identify molecular structures that would inhibit viral growth of SARS-CoV-2. And so predictions made by the model actually fit readily into experimental screens. And those experimental screens in African monkey cells and then human cells revealed that predictions made by the model led to near 62% success rate, rather than a 0.0 success rate that would be obtained by non-guided screening of predicted drugs in an exhaustive manner. And so this is great from the predictive performance standpoint. From the scientific principle standpoint, what we were interested in knowing is whether those predicted drugs that reduce infection in the lab have some common mechanisms of action and that were also predicted correctly. And so what we found is through the use of GNN explainers, through the use of thoughtfully designed visual interfaces, that the way those drugs works is by targeting proteins that are in fact not directly associated with the proteins attacked by the pathogen, but there is a cascading effect of those protein interactions that finally tell us about how the drug exerts its therapeutic effect on the pathogen. And so that is kind of an example that where visualization paired carefully with explainability algorithm has led to this realization of a group of drugs whose therapeutic action is primarily driven by network effects, which we refer to now as network drugs. A follow-up on that study focused on a broader range of diseases is actually a study that I was very fortunate to collaborate with Niels Gellenberg's lab and Sean Ren, and that is presented at VIS this year, that I would highly, highly recommend everyone to check out, which is very exciting. And look forward to the discussion now.
Oh, yeah, thanks for all the panelists for this super exciting presentation. And yeah, I'm very excited to start the discussion. I think maybe we can start with one question in the Slido. So what visualization can play to help the domain experts to calibrate their trust for the AI predictions? And also, I think in many applications, it's more than just calibrate trust. It's even about validate the AI predictions, the knowledge that AI tell humans.
I guess I can try to tackle that first. So I think that when they're trying to kind of understand what the AI is doing, typically if there is some sort of visualization that's trying to explain what the algorithm is doing, that can be really helpful, because if they see that it's like, for instance, listing features that are not relevant at all to what their clinical expertise would consider to be important, they might then decide to overlook the AI and distrust it. However, if it is kind of showing them some features that do kind of correspond to, oh yeah, this is why these things are actually meaningful, these are typically the things that I would also use to make my decision, and that can help them kind of more calibrate their trust. And so we've seen that sometimes it isn't, though. Yes, they are technically visualizations because they might be, bar charts or scatter plots or simple types things. But sometimes it's usually like, what is the information that's getting extracted from the explanation that you can then visualize? And sometimes those things are kind of relatively simple. So often the visualizations are complex, but it's information. The one thing that I will say, though, is that oftentimes, these AI explanation techniques, like, things like SHAP and LIME get applied, but they all kind of have their own uncertainty involved. Are they actually showing things that are relevant or not? And that's something right now that I think the visualization community hasn't done a great job of. How do we actually visualize kind of the uncertainty of these features that are being shown? Are they actually relevant to the prediction, or are these kind of side effects that are happening? And so I think there's a lot of interesting room for research to kind of go from there. With that, I'll be quiet and maybe let some of the other panelists chime in that were nodding their heads.
I could add a little bit here, maybe relate to the challenges we had that I hinted at in my presentation, where we've tried to work a bit in the point of care setting where people are trying to interpret the results of models. And from our experience, they need the visual representations need to be very simple and very quick to use. And I think there's a fundamental tension to some degree between this idea of explaining a model so that people can interpret it correctly and judge it and all the kinds of things that we might think of with explainable AI. And then also the time pressure and simplicity that is kind of demanded in most clinical workflows where you're at the point of care. And that's where I think for us, we've had our best success with population health researchers who have time to dig into the data and think about it long term, as opposed to someone who's really meeting with a patient for 15 minutes and has a lot of other stuff to do. They already have a lot of data and they're already under time pressure. And now you're giving more data. I'm actually collaborating with a urologist here at UNC who's studying the use of risk prediction tools in the context of urology. And he did a major survey of like over 12,000 practicing urologists. And only about a third of them use the risk prediction tools that are there. And of those, most of them trust or half of them trust their own judgment more than any of those tools. And so they kind of dismiss them. And only about a third said they were kind of at all useful. So I think we have a skeptical crowd who is highly trained and expert in what they're doing. And the findings from interviews that this collaborator of mine has, Dr. Ray Tan, is that when the models agree with the clinicians, they tend to agree with the models. And when the models disagree with the clinicians, they tend to assume the model is wrong. And there are lots of ways it could be wrong because the data is really complicated and they don't see the details. It's not like a chemistry test where the chemistry has been proven and reliable and they can do it over and over again in the same way. And someone earlier mentioned validation, I think, is really going to be key here. But it's hard when the data is a moving target and you're training models on data that changes. So anyway, all of those are complexities, I think, when you try and get into the point of care.
Yeah, may I follow up on that? So I also think that so trust, like David and Adam mentioned, it plays an interesting role, but also connected to uncertainty. I have the feeling that like communicating that as part of our tools and solutions is more relevant to those like model developers, model users who have a training in AI and who can do something with that kind of information, right? But if you're at the patient side or at the doctor side, then it's a whole different story, I think. Like if you would overwhelm the user with all these uncertainties, and definitely there are levels of uncertainties that are added here, that makes it more difficult for the patient. And also, I think it's interesting that you have this proxy situation where the doctor is making a decision based on a system and has to explain it then to the patient, right? So the doctor is also like a person of trust to the patient. So there also this human trust that comes into play.
If I can also add to that, so great points. I see visualization also plays increasingly an important role in mitigating some of the issues that we're seeing in explainability field. So it's been now recognized more and more that there's a large number of explainability methods being developed for various data types, for various situations. And some of the challenges that we see is that we are essentially developing another kind of black box model to explain the first black box model. And so studies have been made across different use cases showing how many of the explanations provided by these explainers are not really faithful to how the underlying machine learning model works and what kind of predictions is made. Another very important problem of these methods, which has been alluded by other panelists, relates to just robustness and stability of explainers. Many explainers are actually algorithms that are statistical in nature, meaning if you would explain the same data point or prediction multiple times, each time you would get slightly different explanation. How could that be, right? And so those kind of issues with explainers, particularly post hoc explainers that are trained in a post hoc manner after the ML model is developed, I think that some of these challenges can be addressed and mitigated more effectively with visualizations. Either that can enable us better model debugging and auditing of models, which can be done with data visualization techniques, specifically automated workflows. Many of the studies or explainers, the way they are evaluated nowadays in the literature is through cherry-picked case studies. I would say even my group has done that in the past, and it's not in any. It's because there are little visual frameworks that would allow us to more systematically, comprehensively evaluate those explanations. And the second use case I see as a role for a visualization in explainability and in trustworthy AI more broadly is really to be able to make sure that all facets of explainers are shown to the user. And that primarily goes to the question of uncertainty and being able to flag whether the data is unreliable, or the prediction is unreliable. But that, in addition with model debugging and auditing, is very appealing and something that I find very important to move the kind of trustworthy algorithmic field forward as well.
Yeah, I also agree. I feel like the disagreement between models and users, and even the disagreement between different explanation methods, is really something that a human might want to get involved. We also get a similar question from the Slido from Mark, which said previously work has described issues about immediately providing explanations. And David also mentioned something like, like when the expert says explanations that are different, they just don't trust them at all. And so how can we simulate experts' critical thinking before showing model explanations to better surface the model and user disagreements, and maybe to better understand the reason of these types of disagreement?
It's a good question. I don't have any answers to it. I think, I think the time pressure on at the point of care is really critical, in that it's hard to, in my experience, to stimulate those kinds of kind of deeper reflection and spending more time on stuff. I do think people do it when they're unsure and uncertain, and they'll ask for other opinions and talk to colleagues. We hear all about that. But I think in those same situations, they're also skeptical that the AI is going to be able to give them some magic answer. I don't know. I don't have an easy answer.
For me, one of important questions I ask myself when we work on research project is, who is end user of our tool that we are developing? And so it's very different if the end users are other scientists who are developing machine learning algorithms, who work daily in PyTorch or some other deep learning frameworks. They actually want to see the disagreements, because that can help them understand failures or successes of their methods, or understand what are parts that the method, or what kind of inputs the method works well or does not work well, or if there are disagreements between different explainer methods or different ways the model can be trained, how to mitigate those issues. I see that as a very important part of developing the model in a kind of rigorous way. On the other end, if end users are then biomedical scientists, that's a different user base. And that's also very different from perhaps clinical settings, which is what has just been mentioned, where there are other important properties such as near real-time kind of interventions or interactions with the system, which is something that perhaps it's not absolutely crucial for a scientist who's working in a wet lab in an academic setting. But for them, it might be more crucial to be able to have a tool connected with, say, PubMed literature, so that you can very easily highlight quickly and bring up relevant published literature. So especially in my lab, when we are thinking about ML models and then tying them with their outputs or visual interfaces, the first question we ask, and perhaps the most important for us, is who are the users and what are their needs? And then that informs all our work essentially in that area then.
Yeah, maybe one aspect to add. So that I definitely agree that it makes a huge difference depending on the audience you need to cater to. But then you also have the thing that individuals work completely different, like how they comprehend information. And I'm not sure, because Adam also mentioned, or it was mentioned before, that like explanations need to be deterministic, right? But I'm not so sure about that. If you think about complex theory that you explain in class to students, for instance, you wouldn't pick the same way of explaining it like if you do it a second time, a third time or so. So, and maybe that doesn't even hurt because there are students that would understand the first explanation better than the second explanation, right? It adds some kind of like this human aspect, but I'm not sure about that. If that's a good thing or a bad thing, if it's a feature or a bug, if you cannot repeat the explanations.
Yeah, I think it's an interesting comment. I guess one thing is we'd want to, if there are kind of competing explanations, let's say, we'd want to at least be sure that they're leading to the same types of decisions, right? That they're not, you show them one explanation, they do something totally different than a different explanation. That'd be really bad. But if the explanations are kind of alternative ways of understanding them, that's probably a good thing. And so I think that's what kind of where the kind of current research lacks is like, what are the effective ways of explaining things that people actually, I think it's just a very understood problem. And so I think there's lots of rich research to do from there. So,
Yeah, great. I think, yeah, just a lot of interesting discussions about explanation. But now let's talk more about the visualization part. Yeah, I think as a visualization researcher, like most of our audience are, people are curious about what type of role visualization are playing and also more about how to contribute to those interdisciplinary research, because sometimes it happens or not that the domain experts just want something that is very straightforward. They just want a simple explanation. They want a simple visualization to draw some bar chart for the explanation. And what type of visualization research can actually contribute?
Maybe I can start. I think as a community, the visualization community is doing a fairly good job in addressing like those black box problems, right? Where we like look at the architecture, at the neuron space, and so on. But if you go to the end of the pipeline, to the lay audience, to the people who don't know much about it, which could be even decision makers that make important decisions, right? I don't know why we don't deliver there, or I have the feeling that we don't deliver there as much as we do for the other side. But my feeling is that it could be that the visualizations we need to create are not necessarily interesting for us as a VIS community, and that like it's a problem on its own. Or how do you see that?
I think there's some truth to that. I think if we think broadly about this domain, there are lots of areas where more sophisticated visualizations and lots of user groups, to echo Marika, I'm thinking about who your user population is. I think there are plenty of places where the visualization itself is an interesting problem for us, where we can work. But I do think that in certain populations, that simpler is better, and it does mean that sometimes the visualizations themselves are not interesting, maybe. But I do think there's also a lot to understand in how people react to those visualizations and how they can be mediating tools to understand the underlying models, even if the visualizations themselves are simple. And so maybe it's really studying people and how to understand their reactions in this data environment to the decisions they make, even if the resulting graphic won't be something novel. But the overall workflow and how the context in which you surface information and how you use that to influence essentially the decisions that people are making based on the data, I think there's still a lot to understand there.
Yeah, and I think it's also partly because, we're kind of right now still in this, wild west of like, we have all this complex multidimensional data from healthcare, which is noisy and it has lots of interesting properties and has to be graded. And so there's lots of really interesting kind of computer sciencey problems about how do you take this messy data and kind of organize it in a way that's useful, and you can feed into a model, and then how do you get it into a good model, then how do you get it out of the model, and all this stuff. It takes up a lot of interesting effort. And so I think really the question sometimes is, so the thing that we sometimes maybe don't focus on is, how do we present it downstream to the user? But I also think that sometimes that presentation part is definitely very useful. We need to figure that out, especially when it's going to impact decision making. But I think right now, at least from my side, still the open challenge is how do we get the data out of all this messiness that is the useful thing that we want to display. So even before we can figure out what is the best way to display it, we need to figure out what is the data that we actually need to show. And that's where I think a lot of us are trying to figure out that. And sometimes you need these really complex visualizations to be able to audit the data and figure out what's going on and audit the models and so on, which certainly we do not want to present to doctors at the bedside, right? But we're still not quite there yet to, I think, even know what do we want to present at the bedside.
Yeah, I totally agree. There might be a lot of work and a lot of collaborations need to be done with visualization researchers and domain experts. And especially, yeah, I think talking about that, like, is there any familiar stories that you have ever experienced or like you want to share with us that because of the wrong problem task, because of the wrong assumptions about visualization that, you know, things just didn't work out?
I don't know that I have an utter failure story to share, but I will say it's probably happened many times, multiple times, where I've talked with a clinician and we've looked at how to look at data, and they always push back that it should be simpler and that they have too much to look at. But often then it results in a redirection of this kind of view is really interesting. I would love to look at this as I do my research, or similarly, I could see this being really useful as a patient physician communication tool, where at the point where they're having a discussion about what the data is telling them about what the patient's condition and what choice they might make out of a treatment, that this visualization would be something they'd want to point to help a patient understand as a visual aid. And so maybe the failure is that redirection of it's still too complicated, but there are these other places where I think it could be useful. I've definitely had that happen multiple times.
Yeah, we saw a similar case. So we designed a nice XAI interactive tool, and in the end, and we thought it could be used for multiple types of audiences, right? But then it turned out that it's like too complex for the ones and too simple for the others, right? So I think it would really need different tools, like even in the same project, if you have collaborators and your collaborators are like having different backgrounds and they want to do something differently with the tool, then it's very hard to squeeze that into one UI because it will complicate the exploration experience or the usage for the others. And that's kind of a failure we encountered. Because in the end, you have this very complicated user interface and you say, yeah, if you're that user, you need to use these features, which is not working out.
Okay, go ahead.
Yeah, again, I guess one thing that has come up a lot is I think when first started working in this healthcare field, one thing that often we try to do is, would it be helpful if we kind of summarized, what typically happens to a patient like yours, and what would be the typical thing that other doctors might do to help treat this patient? And if you present that, maybe that would help inform doctors. But doing lots of interviews and working with doctors, oftentimes they didn't really care about how other people would treat their patients, but they kind of view themselves as, well, how would I treat it? I'm kind of exceptional in different ways. I have different skills and expertise, and why would I want to know how other people treat it? That's not really relevant to me. And so I think coming up with this interesting thing that, maybe showing them retrospective data performance is not actually what's useful to them, but they need something else. And so we're still trying to figure that out. But I think that's at least been kind of one lesson learned, is that oftentimes doctors don't always care what other doctors have done in the past. And so what can you actually present to them that would actually be useful is something that we're still trying to figure out.
Okay, so I think we have talked a lot about how visualizations can help explain those AI predictions, and we also have a question from Slido which asks, can those explanations and maybe with the visualizations driving new discoveries in the field of medicine? And Veronica, do you want to start this question?
It's a great question. I think much of the field is driven by the hope that this can be really done. I think right now we're at the stage where we have various one-off studies that are primarily due to a close collaboration between a computational group and a biology or medical group. I think a big question moving forward is to what extent these methods can be more practically be integrated into everyday workflows and be more routinely used. And there are several gaps that would need to be solved before that can be really done. But generally, I'm very optimistic about how then visualization coupled with other aspects of ML, not only explainability can lead to scientific discovery. I think that there is lots of opportunities in the context of just a data collection, data labeling, where then visualization techniques can help us identify what is the right data or perhaps most useful data to train machine learning models on. They can help us label or annotate the data even in a noisy manner very quickly. So there are many other facets of machine learning lifecycle where I believe visualization can be helpful not only to visualize part of the data, but really help accelerate again kind of the workflow being implemented or even just solve crucial bottlenecks there. So I'm very optimistic about that, but we are certainly at this relatively early stage where it's not really clear how to go from what we have to everyday routine implementation of many of the techniques. And I hope that this is something will happen in the coming years.
Okay, I think now is almost the end of the panel discussion. I think some questions for a more summarizing purpose. I think the first one is, again, a question from Slido. What would be the advice you want to provide for some young researchers who want to join this field? What's the most important thing that you think they should know?
Just one quick kind of thing is like find a clinical collaborator that you can work with. Make sure you're working on something that's actually really like impactful and relevant to what they're doing. I think we see a lot of interesting research that sometimes doesn't quite map to what these user needs actually are. And so working with finding them is definitely step one for sure.
I would just agree. I think finding collaborators, if you're an outsider to any discipline, finding a collaborator who understands the work, and then I think will give you a head start into trying to create solutions that are useful for people. And I think it's an exciting place to work because the challenges are really hard, as we've been talking about, and hard problems lead to good research problems. So I encourage people to do it, but definitely finding collaborators is really helpful.
Yeah. And I think those collaborators should, like, one, have time to collaborate with you, and two, should also like acknowledge what you do. And that's super important, because if they just think of you as like adding the nice UI, the nice looking UI to their great research, then it's probably not the right collaborators, right?
Yeah, thanks. And one last question. And so what do you think, like most of you like are excellent researchers in this field, and what do you think would be the most promising future directions? And what do you think is the most critical challenge that the current visualization research must make to get there?
We're all jumping on this one. I think there are a lot of challenges. I think the ones we've been talking about are right up in there. I think figuring out how exactly these great tools can solve real problems is the summary I guess I would use for all of these problems, whether it's a doctor in the emergency room or whether it's a pharmacologist studying a new drug, and figuring out how to get these tools in a way that actually fits into the workflows that people do. And it's really complicated. So I think I think most of it fits into that category.
Yeah, I think that like the less a problem can be automated, the more visualization can contribute, right? Because if you're almost at the point where you have a fully automated system and you just need to like output the final decision or the final decision with some uncertainty, but then that's it, and you can't like overwhelm the user with more complexity, then what's the value of this there? So I think it's really about when you think about AutoML and like those closed loops, and you try to open it and look for places where interactive visualization also can contribute. And I think that's a very interesting future direction.
Adam or Marinka, is there anything you want to add?
I agree with everything that was said. Perhaps just to add to that, I think visualization of physical systems to me is very an appealing direction. And by physical systems here, I mean, in the context of particularly my research, that would mean visualizing proteins, visualizing cells, visualizing the spatial samples that would require us to be aware of the underlying geometry and structure and in three-dimensional space within which a particular molecule lives and exists. In addition to visualizing knowledge graphs, which are more abstract objects not found in a physical space. I also think that the question of now increasingly these physical instruments that we have going from Large Hadron Collider generating hundreds of terabytes of data per second to lots of biological high throughput experiments really raise the question of identifying interesting, relevant part of the data for downstream analysis. So that often requires us to look at the data at multiple different levels or scales. And so here I think visualization can be really helpful in terms of identifying what is the right appropriate scale to look at the data, coupled with, say, ML or other techniques. Yeah, those are two directions that I like a lot.
And yeah, then maybe I can just close with one other, I think, big open challenge that we didn't really have too much time to discuss today, but we are kind of working in this domain where there's lots of high stakes decisions that need to be made. And so how do we also kind of effectively validate that the stuff that we're doing is actually helpful and not harmful? And I think letting us thinking about, you know, how would we want to validate this to work in a way that is meaningful? And I think a lot of times when we talk to doctors about would they adopt our tools and techniques, they're like, well, if it was published in JAMA and it showed that this had this validation, then sure, we would take it. But until that, we're going to ignore it. So I think for us to think as a community about what are the right ways for us to kind of ensure that what we're doing is helpful. So.
Yeah, that's great. Okay, it's already 12:02 now. And thank you so much for this panel discussion. And this is the end of our workshop. And for those who are at Oklahoma City in person, yeah, we have those launch meetup, and you can find Niels and BC to join us. Okay, that's all. Thank you so much.
Thank you very much.
Thank you.
Thank you all.